talking about some probability. So, find the fourth term of this expansion. So you know that if you were going to expand this whole thing, the first thing you would do is write down the 8th row of Pascal's triangle, right? Now, I do not have the 8th row memorized, and so if I'm going to do it that way, I'm going to have to start building Pascal's triangle. Remember how we did that? Start with 1, 1, and then add these two together, so that's a 2. Add these two together. I mean, this would be how you would build it. Remember how you add those numbers to get the 1 underneath? And I would have to go all the way to the 8th row. I do not want to do that. Who remembers the other way we have of finding the numbers in Pascal's triangle?
Isn't it like 8,
Yep, it's the combination numbers. So if you want the 8th row, the first number in the 8th row would be 8C8. Which you have a calculator, you can type that in 8C8. And then 8C7, 8C6, 8C5, and so on, all the way down to 8C0. Now, the only one I want in this problem is the 4th one. So 1, 2, 3, 4. So my number is 8C5. So you can either build the whole triangle down to the 8th row, and that's perfectly okay. It takes forever and it's great big. But you can do that. Or you can remember that the 8th row is the 8C numbers. 8C8, 8C7, 8C6, da 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 da. The 4th one is this. So I can get that on my calculator. 8C8, or 8C5, I'm sorry, 8C5. I got 56.
Yep.
So pretend I have all the numbers written out. One of the numbers in the line would be 56. Next to all of the numbers, I'm going to have an X and a negative 2Y. Agreed? Next to all of them, I'm going to have that. But I'm only caring about the 4th one. Then I'm going to put my powers on. Well, in the very first number, the power on X would be 8. So it would be 8, 7, 6, 5. So the power on my X is 5, which means that the power on my Y has to be 3. So I know I'm going to have an X to the 5th and a Y to the 3rd. My numbers are 56 times 1, there's no number there, it's just a 1, times what here? Negative 8. Negative 2 times negative 2 times negative 2. So 56 times negative 8, negative 448. There is the answer to the question. Okay? That's review from last time. Now, the new part that we're doing here, number 3 in section 9.2, says evaluate by hand. What in the world does this even mean? Well, I'll tell you what it means. It means 7C3. So another notation, C's, combinations are used so much that there are different notations for them. Certainly this is one notation, this is what's on your calculator, but this means the same thing. This means the combinations of 7 things taken 3 at a time. These are exactly the same. Now, I know you could plug that in on your calculator. In fact, go ahead and tell me what you get. Tell me what you get when you type it on your calculator. What? 35. Now, how did that 35 come about? What math is the calculator doing? Well, I'll show you. 7C3 means 7 factorial over 4 factorial, 3 factorial. Okay, now wait, Mrs. Ford, wait. The 7 is right here. Okay, that makes sense to me, okay. The 3 is right here. Okay, that makes sense to me. Where did this 4 come from? What?
It adds up.
7
Oh,
minus 3. 7 minus 3. So when we build one of these by hand, if you have your calculator, you just type it in and you're done. But if you have to do it by hand, then you're going to set it up as this number factorial over this number factorial and also over the subtraction factorial. Okay, so this number's on top, there's 2 numbers on the bottom. Okay, now, wait, Mrs. Ford, I have to do this by hand. You mean I can't type that in on my calculator? No, but you don't need to. Watch this. Who remembers what 7 factorial means? 7 times 6 times 5 times 4 times 3 times 2 times 1, right? And 4 factorial means 4 times 3 times 2 times 1, and 3 factorial means 3 times 2 times 1. Now look at this. See this part right here? Isn't that all going to cancel? Yeah. And 3 times 2 is 6. So that's going to cancel with the 6. And what's left? 7 times 5, which is 35. So you can do that by hand. And we're going to practice a couple more by hand. HC3, set it up for me. What's that going to look like in terms of this setup?
8 factorial.
8 factorial. This number on top, factorial.
3 factorial.
Over 3 factorial, that's this number. But also over 5 factorial. These 2 minus each other.
Does it matter the way that the 3 and the 5?
Nope.
Okay.
The order of the 3 and the 5 does not matter one bit. Now, let me show you something else that might be a little bit of a time saver. I'm not trying to confuse you. But I'm not going to write out 8 factorial. That's a big number. I just did 7 factorial. I'm not going to write it all out. But I'm going to say 8, 7, 6, 5. Because what's going to happen on the bottom down here? Aren't all those going to cancel? Yeah. Everything from the 5 on is going to cancel with this guy. So all I have left on top is 8, 7, 6, and all I have left on the bottom is 3, 2, 1. If that confuses you, write it all out like I did here. Write it all out. But with all these problems, at some point, canceling is going to happen. And in this case, it happens starting with the 5. So again, 6 and 6, it looks like this answer is 56. Check it on your calculator. 8C3, I hope it says 56. Does it? No one even checked. All right, 100 C98. Whoa, whoa, whoa. There is no way I'm writing out 100 factorial. 100 factorial over 98 factorial 2 factorial. Would you agree with that? Now, 100 factorial means 100 times 99 times 98 and so on. But everything from 98 and so on is going to cancel. Agreed? So all I have left in the bottom is 2 times 1. So 2, if you want to continue canceling, 2 will cancel into 100 and leave 50. So 99 times 50 is going to be our answer. So 4950 is the answer to the problem if I applied right. See how that cancellation works, kids? It happens every time. All right, would you try D on your own? See if you can get D. 11C6. Oh, I guess we have two more. We'll do 11C6, see if you can get that one. Did you get everything from the 6s on to cancel?
Yeah.
But you still have a 5 factorial left in the bottom, so you still have all this left in the bottom. Now, you can do a lot of canceling here. For example, 5 times 2 is 10. And 3 will go into 9 3 times. And 4 will go into 8 twice. Your whole denominator should always all cancel out. So it's all gone. I'm not worried about the 1. It's all gone. So what's left is 11 times 3 times 2 times 7. So you can do that however it works for you. You don't have a calculator. You don't have to multiply. But 3 times 2 is 6. So 66 times 7. I got 462. If I multiply it correctly. We love our calculators, for sure. But you need to know how to do these basic ones without. Okay, 10C7, last one, then we're gonna start some probability today. 10C7. Michael, can you figure this one out for me without a calculator? What was, yeah, start with the setup. Yep, that's right. What would the setup be?
10 factorial.
Yep.
Is 7 factorial and 36.
Perfect. That is exactly right. That's exactly right.
You did.
Now, when you start thinking about 10 factorial, which is 10 times 9 times 8 times 7 and so on, isn't the 7 and so on all going to cancel with this guy right here? And all I have left in the bottom again is my 3, 2, 1. Are you following that? I'm not pulling a fast one on you, right? You get that? So canceling here, 3 goes into there 3 times, 2 goes into here 4 times. I got 120 if I multiplied right. Okay, everybody all right with that? All right, good deal. 7-2 homework will be due, forever from now. Let's see. Today's Thursday, but we're not in school Friday or Monday, Tuesday, Wednesday, so it's due Wednesday, next Wednesday. You have almost a week to get 7-2 done. If you do it over the long weekend and you want to email it to me, that's fine. Turn it in whenever, next week, Tuesday or Wednesday, that would be great. All right, so now we're starting probability, which is going to be a much bigger section, lots and lots to do in probability. We're going to look at several kinds of probability situations. The first kind we're looking at here is with just a probability table, just a chart. So, Maggie's got a bag of M&Ms and Elizabeth has a bag of M&Ms. Okay, they opened them up and they counted them out, and Maggie discovered that 30%, 30% of her M&Ms were green. Are there green M&Ms?
Yeah.
Are there? Okay. And 20% were yellow and 20% were red and so on. Elizabeth did the same thing and she got her percentages. That's what's happening in the chart. Okay? Now, you walk into the room you walk over and grab an M&M out of Elizabeth's bag. What's the probability it will be green?
2%.
Not 2%,
No.
20%. 20%. Because 20% of Elizabeth's M&Ms are green. That says that in the chart. So if you reach in and grab one, you have a 20% chance of getting a green M&M. So the answer to A is, you can say 0.2, you can say 20%, you can say 0.20, whatever, as long as it's the equivalent of 20%. Now, somebody else walks in and grabs an M&M out of Maggie's bag. What's the probability it won't be yellow? What? 80%. Because in Maggie's bag, 20% of them are yellow, which means 80% of them aren't. So your probability of getting a not yellow would be 80%, or 0.8. Now, we're going to take an M&M from each bag, and we want them both to be red. So in other words, we want red and red. Who remembers what we do in an and problem? Multiply. This is going to be a multiply. So what's the probability of getting a red one from Maggie?
20%.
0.2. You can say 0.2, you can say 20%, whatever works for you. What's the probability of getting a red from Elizabeth? 0.3. Now be careful, you'll have a calculator, use it. When you multiply these, you don't get 0.6, you get 0.06. Let your calculator do the work if you are uncomfortable multiplying decimals. Okay. What am I ready for? D. What is the probability that neither will be brown? So again, we're taking one out of each bag, and we want not brown and not brown. That's what we want. We don't want any browns. So what's the probability of getting not brown from Maggie? Huh? Probability of not brown is 0.8 from Maggie, and, which means times, not brown from Elizabeth would be 0.9. So your probability is 72%, 0.72. Candy is chosen from each bag. What's the probability that the first one will be green and the second one is blue? Okay, so first one is green. So that would be 0.3. And then from Elizabeth, I need blue, so that would be 0.06. Again, 0.3 times 0.2. You okay with that? Yeah, pretty easy. Now the next one's a little challenging. What's different about question F than question E? Because I'm still getting a blue one and a green one, but what's the difference? The order. Because in question E, it says I have to get green and then blue. But what could happen in question F? I could get green and then blue, but I could also get blue and then green, couldn't I, in question F? So I think question F says green and blue, or blue and green. Read question E carefully. I know. question F. Read question F carefully. Is this what it says to you? I could get a green one and then a blue one, or I could get a blue one and then a green one. Because I just want to end up with one of each. Well, this we already did. This was 0.3 times 0.2, which was 0.06. Or, okay, now what's this one going to say? Blue and then green. What's that? Blue from Maggie is 0.1 and green is 0.2. So that's 0.02. Now it's this one or this one. What do I do in an or? I add. That's an add. So the final total answer is 0.08, 8%. Remember, and you're doing this and this, you multiply. If you're doing this or this, you add. Okay? Your test will have a chart on it, like this, and you'll have some questions like these. All right, let's see, there's one more. If a candy is chosen from each bag, what is the probability that neither will be red? So I want not red and not red. Okay, what's the probability of not red from Maggie? 0.8. And, which means times, not red from Elizabeth would be 0.7. So the answer is 0.56. There's a 56% chance. Now, there are many kinds, many strategies to approach probability with. Some probability problems have what's called a probability chart. That's what we just did, the M&M chart. There are other ways. David, my friend, put your phone away. You can do that wherever you're going, but don't do it in here. Thank you. Have a good Easter. All right. And is and. Okay. Now the next set of problems here are going to deal with cards. We're going to do card problems. Okay? They're going to be done differently. Obviously, there's no probability chart. I'm not building a chart. It would be absolutely gigantic. We're going to do this a different way. So, letter A is not a probability question. Letter A simply says, I'm going to deal you a 5-card hand from a standard deck. How many hands would be possible? Well, how many cards are there in the deck? 52. 52 cards in the deck. How many am I giving you? 5. So it's like I have a group of 52, and I'm going to pick 5 to give to you. Does the order matter? So that's 52 C5. That's how many 5-card hands are in the deck. This is the total number of hands in the deck, 5-card hands. The total number of 5-card hands in the deck. That's a big number. There's a lot of them. Now, what's the probability that those 5 cards I give you are all diamonds? Now, do you understand that probability is a fraction? And the denominator is the total? And the numerator is what you want? In math class, we're supposed to call it successes, but it's what you want. So we want, our number, letter B answer is going to be the number of ways we can get all diamonds over the total. Well, guys, you already know what the total is. How many total hands are there? 52C5. That's the denominator. So for problem B, I already know that my denominator is 52C5. In fact, that will be the denominator of every card problem that involves a 5-card hand. That's the total.
Why don't we type the 52C5 into the calculator and then?
Oh, I didn't do it here? Yeah, you should. I mean, obviously you need an answer written down, but we have typed so many into our calculator that I think you know how to do that, right? Yeah. This one I will type in because this is gonna be a division problem. We've not done that yet, so we're gonna go ahead and do that. But first I need to figure out what my numerator is. How do I get all diamonds? Now stop and think about it for a minute. How many diamonds are in the deck? 13, and you still want 5, right? So your numerator is 13C5 because there's 13 diamonds and you're picking 5. That's what you want. But the total is 52C5. Now, nothing cancels. Do not even think about, canceling 13 into 52 or something weird like that. No, no, no. We're going to go to our calculator. 13C5, and then just hit divided by 52C5, and you get something that looks like this. Now we need to talk about it for a second. Okay, did anybody else get that? Now remember when the E pops up, that's scientific notation. So this means 4.95 times 10 to the negative 4. Which means 4.95, but moving the decimal 1, 2, 3, 4 places. Fill the shells with eggs, and our number is 0.000495. So the probability of you being dealt an all diamond hand is 0.000495. In other words, it's not very good. Your chances of getting all diamonds is not very good. Okay, so let's back up, because there's a whole bunch of these. Let's back up. Does anybody have a question about the basic setup? How we got 13C5 and how we got 52C5? Is the basic setup okay? Roxy? There's 13 diamonds in the deck. This is an all diamond hand. There are 13 diamonds in the deck. Avery.
Sorry.
Turn it off. Put it in your backpack. Don't let it tempt you. All right, so we're okay with the setup. Now, this is one that I could do out by hand with factorials and all that, but it would take a long time because these are huge numbers. So I'm not going to do that. I'm going to type it straight into my calculator. I typed it in just like this, and I got this answer, which I have to recognize when that E pops up, that means your scientific notation. And then that doesn't mean anything to me, so I write it out as a decimal by backing up the decimal point 4 places, and that is the answer to the question. So if this is a quiz or a test and there's an answer blank, that's what you write down. That's the probability. All right, what's the probability of being dealt a hand with all face cards? All right, we'll stop. What's the denominator? 52C5. 52C5. this set of problems, consider being dealt a 5-card hand. All your denominators are gonna be this. That's the total hands. And in a probability question, total goes in the denominator. All right, now all face cards. How many face cards are there in the deck? I heard somebody say 12, and that's right. Remember, the face cards are Jack, Queen, King. 3 of them, hearts. 3 of them, clubs, spades, and diamonds. So there's 12. So this denominator is 12C5. 12 face cards. This is going to be an even smaller number. 12C5 divided by 52C5. Always be careful, guys. Pay attention for that E. Look for that E. That's your scientific notation. So this is 3.047 times 10 to the negative 4th. So we're gonna write down 0.000305 if we round it off, or 3047. That's your probability. Roxy?
The cookie, and then it ends.
Huh?
And then it ends.
Did you press like?
I don't know what was that? Was that the division sign? No, try it again. You shouldn't get an error.
It's like how when you put in a exponent, you have to like.
Oh, yeah, tell them, yeah.
Yeah.
So it's keeping everything down low
Mhm.
instead of putting it back up. Yeah, so you guys with the newer calculators, got it figured out? Are you getting the right answer? Okay. All red. What's the probability of getting an all red? Well, your denominator is 52C5. What's your numerator gonna be for an all red? 13C5? 26C5. Because aren't there 26 red cards? 13 diamonds and 13 hearts? Again, do not think you can cancel and get a half or something goofy like that. No, 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 no. You gotta type it in. There's nothing to do but type it in. Now there's no E in this one. The answer is just 0.0253. And you'll have rounding instructions, so don't get hung up on that. Are you getting 0.0253? So if you were dealt 5 cards, the probability of you getting all red would be about 2.5%.
For some reason, when I put that in, I got 1.2.
Oh, maybe I copied it wrong. No, try it again. It's 0.0253. All right, letter E. What's the probability? Denominator 52C5. Numerator is 3 jacks and 2 kings. What's that and mean? Multiply. So I'm going to have a couple of things multiplied. All right, so I need 3 jacks. 4C3. Now, let's make sure everybody's on board with that. I want 3 jacks. How many jacks are in the deck? 4. I have to pick 3 of them. 4C3. I don't care which 3. These are all going to be C problems. You don't care about order. But 4C3. 4 jacks, pick 3. Again, if you're not comfortable with the deck of cards, spend some time this weekend getting comfortable with it. You don't have to play any games, just know what you got. Now, I want 2 kings. What's that gonna look like? 2 kings. 4C2. There are 4 kings. You're gonna pick 2 of them. And you're picking 3 jacks. So those are getting multiplied. These are the jacks. These are the kings. They're getting multiplied. So we can do that on our calculator. 4C3 times 4C2 divided by 52C5. If you want to do that, in separate steps, you can, but your calculator will do this whole thing at once for you. I got an E, did you notice? You got an E. So it's 9.234 times 10 to the negative 6.
Yeah.
So 1, 2, 3, 4, 5, 6. So the answer to that one is 0.000009234. Does, even if you don't know much about cards, does the fact that you got an extremely small number make sense in this problem? Yeah, if you're just randomly dealt a hand, the chances are going to be low of your getting exactly 3 jacks and exactly 2 kings, right? Yeah, not gonna happen very often. All right, F. What is the probability of being dealt a hand with no face cards? Okay, so no face cards. So denominator is 52C5. Denominator is always 52C5 if you're picking 5 cards out of the standard deck. Earlier we had a problem with face cards. How many face cards did we say were in the deck? 12. So how many not face cards are in the deck? 40. So isn't our numerator just going to be 40C5? Does that make sense to everybody? If you pull out the face cards, you're going to have 40 cards left to pick from. So 40C5, bless it, divided by 52. You get 0.2532. Again, don't worry about the rounding. Make sure that's the number you're getting. Is that what you're getting? So that means that if I randomly dealt you 5 cards, there's about a 25% chance that you won't get any face cards. All right, G. Denominator is 52C5. Now the numerator is, what's the probability of being dealt a 5-card hand and getting all of the aces? Not very good, right? But what is it? What would the number be? Well, what do you think? What? I heard somebody say something. 4C4. Okay, how many aces are there, kids, in the deck? 4. We need all of them, right? 4C4, gotta pick them all. Here's where this problem gets tricky. How many cards are you being dealt? 5. What does that mean? You have all the aces, but what else do you have? Some other random card? So what's happening is you're getting 4 aces and 1 not ace. Do you understand that? So 4 aces is 4C4. And means times. Now, how many not aces are in the deck? 48. And you need one of those too. To complete your 5-card hand, you need that fifth card to be something other than an ace. Does that make sense to you? What makes this problem tricky is they don't mention this. You have to figure that out on your own. It's a 5-card hand. 4 of them are covered by the aces, but the 5th one has to be something else. And it's an and situation, so we're multiplying. All right, so here we go. I got an E. Obviously, I think that's, you recognize the chances aren't very good. So I got 0.0001847. All right, we're almost done with this set. Now we'll look at a Venn diagram. What is the probability of being dealt having 2 10s, 2 jacks, 1 queen?
Is it kind of like the 3?
Denominator 52C5. Now do one kind at a time. So 2 10s, 4C2. So this is the 10s. There are 4 10s in the deck, 1 of each suit. Diamonds, hearts, spades, clubs. I'm picking 2 of them. All right. How many jacks are in the deck? 4. And I'm picking 2 of them. So I'm going to have another 4C2 for the jacks. And then I need 1 queen. What's that going to look like? 4C1. That's my queen. Now, this hand is 2 10s, 2 jacks, and 1 queen. So what am I doing with all these numbers up there? Multiplying them. Because 2 jacks and 2 10s and 1 queen. What did we end up with? Yep, 5.541 times 10 to the negative 5th. Remember that E means times 10 to that power. So 0.0005541. Yeah, don't worry about the rounding. Is that the number that you came up with? These are all very small probabilities, or most of them are very, very small. Don't bet your allowance on being able to do this. All right, one more. What is the probability of being dealt a 5-card hand with no aces, no queens, no 5s? No aces, no queens, no 5s. Here's my deck of cards. I'm going to take out the aces. I'm going to take out the queens. I'm going to take out the 5s. How many cards are left if I do that? How many? 40. Aren't there 4 aces, 4 queens, and 4 5s? So if I take 12 cards out of the deck, there's 40 left. So my numerator will be 40C5. Remember, your numerator is always what you want. You want to pick cards that aren't queens, aces, or 5s. They're out. this is gonna be a pretty big number. I mean, relatively speaking, it isn't gonna be a big number, but relatively speaking. Oh, is this an answer to another one? 0.2532?
Yeah.
So there's a 25% chance that the hand you get will not have any queens, aces, or fives in it. All right, so far today, we have one more thing to talk about. So far today, we've talked about problems that have a table or a chart given to us. And we've talked about card problems, problems done with C's. Now we're gonna look at problem 3, which is a Venn diagram. You've all seen a Venn diagram before. I'm positive. And what this Venn diagram represents, we're gonna do this problem and then I'm gonna stop, so try to hang with me. What this problem says is, there are 30 kids in the class, so here's the class, the box is the class, there are 30 kids in there. We did a poll about who likes M&Ms, who likes Twix. So M&Ms and Twix. And this is the result of that poll. So the questions are, how many kids like M&Ms? What? 17. Because if you like M&Ms, you're in the M&M ball. And here's the M&M ball. And how many kids are in that? 17. So the answer to A is 17. Perfect. B, how many like only M&Ms? That's 11. Because these kids aren't part of the Twix ball. They're only in the M&M ball, so 11. How many like M&Ms and Twix? 6. 6. These guys right here are part of both balls, right? So there's 6. How many like M&Ms or Twix? Now stop and think about this for a second. Got a classroom full of kids. How many of you like M&Ms? Up go the hands. Okay, I count. Okay. How many of you like Twix? Up go the hands. Okay. Those are the people who like M&Ms or Twix, right? What's the answer to the question?
20.
26. 26 is the answer. There are 26 people in these circles. Now listen, I know which one he's coming from, but I want you to think about this. Everybody in this ball likes M&Ms, correct? Everybody in this ball likes Twix, correct? So if you are in a ball, you like one or the other, and some of you like both, and that's fine, but you like M&Ms or you like Twix, if you are anywhere in the circles. So the answer is 26. How many like only M&Ms or only Twix? That would be 20. That would be these kids or these kids. That would be the kids who only raise their hands twice. Or once, only raise their hands once. How many like neither candy? Or how did you get that? There are 4 kids that didn't raise their hands because there's 30 altogether and 26 are represented here. There you go. Last question for you. I reach into the pool of students. I reach into the box and I grab one. What is the probability that he will like both candies? I reach in, grab a kid. What's the probability he'll like both? How many kids like both? 6. How many kids are there altogether? 30. The answer would be 6 over 30 or 1 1/5. If you want to do it with C's, you can, but it would have to be 6C1 over 30C1, because you're only picking one kick, right? So I think it's easier just to do 6 over 30, but you could do that. All right, kids, you did great today. Good work. We made a lot of progress.